Our last type of calculation in section 7.4 is percent yield. To calculate percent yield, we need to know theoretical yield and actual yield. Theoretical yield is what we expect to get from our reaction based on the amounts of our starting materials and the stoichiometric relationships in our balanced chemical equation. If you were doing a limiting reactant problem, you would take the amounts of starting materials and convert them into amounts of product, and the smallest of the amounts of product is your theoretical yield. The actual yield is what you actually get in the lab. For example, if you're weighing out copper on some filter paper after doing a series of reactions, the mass of the copper is your actual yield. The actual yield is probably going to be less than the theoretical yield because the real world isn't perfect. Maybe some of the copper stuck to the side of the beaker, or maybe it fell through the filter paper and got discarded. You're typically going to get less than what you were expecting to get from a reaction based on the stoichiometry. Therefore, the percent yield ought to be a number that's less than 100%. If you ended up calculating a number of greater than 100%, you likely had impurities. Maybe some water or ethanol is stuck with your product and is adding extra mass to your measurement for actual yield. If there are no impurities, the percent yield will always be 100% or less. Our calculation of percent yield is going to be the actual yield divided by the theoretical yield, that is, what you got divided by what you should have gotten, times 100% to make it a percent instead of a decimal. Here's an example. We're reacting 1.274 grams of copper 2 sulfate with excess zinc. We're told that 0.392 grams of copper metal was obtained. That means that 0.392 grams of copper metal was weighed out on the scale at the end of the experiment. So that's the actual yield. The 1.274 grams of copper 2 sulfate is the starting material that was put in. What we're going to have to do is figure out how much copper should have come out of the reaction based on the amount of starting materials put into it. By telling you that there was excess zinc, that makes this problem a lot easier because it's not a limiting reactant problem. We know that the limiting reactant is the copper 2 sulfate because there was extra of the zinc. That means that based on just the amount of copper 2 sulfate, we can calculate the amount of copper that should form. It will be one calculation instead of two. If we were given starting amounts of both reactants and not told that one was excess, we would need to treat it like a limiting reactant problem to see how much product could form based on the starting materials. To find percent yield, we're going to do actual divided by theoretical times 100. Our actual yield was given to us in the problem. This is 0.392. The theoretical yield we have to calculate. We'll take our grams of copper 2 sulfate that we started with and change it into moles. That way we can do a stoichiometry problem that goes from moles of one thing to moles of another. We're going to go from moles of copper 2 sulfate, our limiting reactant, to moles of copper, the product that we're interested in. Then we go from moles of copper to grams of copper. That way we can compare the grams of copper that we should have gotten to the grams of copper that we actually got. First, we're taking our 1.274 grams of copper 2 sulfate that we're starting with and changing it into moles by dividing by the molar mass of copper 2 sulfate, which is 59.608 grams per mole. Again, check your units. Grams is going on the bottom here to cancel out, and molar mass always goes next to grams. We get 0.007982 moles of copper 2 sulfate. Then we can change our moles of copper 2 sulfate into moles of copper. In this particular balanced chemical equation, there's a 1-to-1 relationship. The number ends up being the same, 0.007982, but the units are different. Now, instead of talking about moles of copper 2 sulfate, we're talking about moles of copper. For our last conversion, we can go from moles of copper to grams of copper using the molar mass of copper. This time the molar mass goes on the top. We're multiplying 0.007982 by 63.546, and we get 0.5072 grams of copper. Our percent yield is going to be actual divided by theoretical times 100. Our actual yield that we got in the lab was 0.392. That was given in the problem. We divide that by our theoretical yield, which we just calculated to be 0.5072. And then we multiply by 100, and that gives us 77.3% as our percent yield. Upon reaction of 15.0 grams of sodium iodide with excess lead to nitrate, 6.00 grams of sodium nitrate was obtained according to the equation Pb parentheses NO3 parentheses 2 plus 2 NaI yields PbI2 plus 2 NaNO3. What is the percent yield? The molar mass of sodium iodide is 149.89, and the molar mass of sodium nitrate is 84.994. Is the answer A, 29.5%, B, 40.0%, C, 60.0%, or D, 70.5%? The correct answer is D, 70.5%. We know that sodium iodide is the limiting reactant, so we can convert from grams of sodium iodide to grams of product to obtain the theoretical yield of that product. Since we know the mass of sodium nitrate that was obtained in the lab, that would be the actual yield of the sodium nitrate. That means we want to pick sodium nitrate as the product we are finding the theoretical yield of. We go grams of sodium iodide to moles of sodium iodide using the molar mass of sodium iodide, then moles of sodium iodide to moles of sodium nitrate using the balanced chemical equation, then moles of sodium nitrate to grams of sodium nitrate using the molar mass of sodium nitrate. That would give us our theoretical yield. We do actual divided by theoretical times 100, and that gives us 70.5%.